Yes.
So hello everyone. I was just mentioning that I'm just impressed about the motivation of the students for this year. We got 21 participants here, which is great. Give me just 5 seconds.
Yes, Wilson, I agree. Also, during office hours, I remember that last year we have 3, 4 participants, and this year we have always 10.
21 participants on a Sunday morning. Happy Father's Day, by the way, because I know that in some countries is the Father's Day today. It's not here, but I don't know in Brazil.
No.
It's not.
No,
okay.
It's not.
Great. So let's start with my presentation because this is going to be, as you can imagine, as we are progressing along the course, it's going to be slightly more complicated and more complicated, but I'm really hoping that you can enjoy my presentation and you can make the most of it. But don't worry if you can't understand all the concepts because, as I say, this is very complex, and then this is the only way to do this 9 months course because I mean a couple of weeks ago we were talking about chi-square and feature square, but this is just for a week, and then we have to make progress with the course because otherwise we can't cover all the topics. So great. Let me just share my screen here. So I can't share my screen, Karla, because I'm not a host. So you might need to invite me as a host.
Yes, I'll do it now.
Great.
Yes, Wilson, please. I guess you can do it now.
Yes, I can share now. Perfect. Great. Good. So I'm going to minimize this. And where is my presentation? So this is my presentation. Great. So I've got for today only 22 slides. Probably I won't have time to discuss all the topics with you because some of them might take me a long time to explain to you, but I will try to cover everything as much as I can. As always, please feel free to interrupt me, ask questions, be really participate in the meeting. This is not a lecture. I want this to be like a meeting with students' interaction in order to increase the to help you to consolidate the knowledge. So I haven't introduced myself, by the way. So my name is Wilson Fandino. I'm one of the TAs too for this course. And at the moment I'm working as an anesthetist here in London, in St. Thomas's Hospital in London in the UK. So just a quick refresher regarding I just like to start with this slide because I think it's important for you guys to keep in the context of the course. So during the first module, we were discussing the recruitment process, the randomization, the blinding, allocation concealment, some ethical issues that you might face with your clinical trials. And then during the second module, we started to discuss some statistical tests that are important for you to understand. This is the third meeting. In the first meeting, we discussed the concepts of homogeneity of variances, the concepts of normality, when to use a non-parametric test, when to use a parametric test, the assumptions for parametric tests. And then over the next weeks, we've been discussing the comparison between continuous dependent variable and a categorical independent variable, by which I mean t-test, ANOVA, repeat measures ANOVA, and all the equivalent non-parametric tests for this particular situation. And then we've been discussing the chi-square, the Yates correlation, the Yates, the Fisher exact test. And then we are going into this part of the course, which I believe is slightly more complicated, but still, obviously, we are able to understand all these concepts. As I say, it's going to be slightly more complicated because I'm going to talk about correlation. The concept of correlation is straightforward, but when we talk about regression, it's going to become slightly more confusing, but I'm really hoping that you can understand with my presentation, okay? Right, so just to start with a little bit of history, we are going to talk about the Pearson correlation. I did speak to you last week about this statistician, which was very important, not only here in this country, but in the whole world. So this statistician was working in the 19th century, and he described the chi-square, but not only the chi-square, he was the first one to describe the correlation, and this is going to, this is why we are going to talk about Pearson correlation when we are dealing with parametric data. And then there's a couple of versions of non-parametrical data, and it actually depends on your research question. If we have time, we are going to discuss about the Spearman correlation, which is the, as I say, the non-parametric version of the Pearson. And there is a special case in which you are interested in finding out whether the ranks of one group are correlated to the ranks of the second group. So in that particular instance, you must use the Kindle, the tau Kindle, that's what it's called. So R for Pearson, RH for Spearman, and tau for Kindle. As you can see, all these statisticians were born here in London, and they were working independently over the last century. For some reason, something happened at that time that in this country, they were really interested in statistics and describing the tests. As you can see, all these statisticians were born here in the UK. But I just can't figure out what happened at that time, that everyone became really, really interested in statistics. Anyway, so right. So before going to this, before going through this slide, I would like you to ask what do you understand by linear regression? What would be, in your own words, the definition for linear regression? And I'm going to see the chat here to see. Any thoughts?
I think when you want to see a correlation between the two groups, and it's not only the dots. When you see the correlation, you put the dots on the chart, and then the linear regression is the line that you put between the dots that has the less size of variance. I'm not sure if it's variance that you said.
Perfect. That's perfect. Yes. So I'm not sure who was speaking, but she was absolutely right. Let me just go back to my slides just to explain to you a little bit more about this. When your independent variable is continuous and your dependent variable is continuous as well, so you must wonder yourself if you should use a parametric or non-parametric test. In both cases, we are talking about linear regression, which is the simplest model of regression, because we also have logistic regression like here, or regression for survival time, which is the Cox regression, and then there's a special case when the dependent variable is count. In which case you have to use the Poisson regression, but this is not covered in this course. So today we are talking about only these tests, which are the R for Pearson, RH for Spearman, and tau for Kendall. Okay, so I don't know who was speaking before.
It was Flavia Wilson.
Flavia, thank you for that. So if I go to my data here, I'm going to generate some data very quickly.
Wilson, in the end of your presentation, we can talk about how interpret the repeated measure ANOVA. I guess in our last meeting, we are not sure about it, and I asked it for a friend, and he taught me how to interpret the outcome of repeated measure ANOVA.
Of course, yes. Because we had some doubts as well regarding which p-value look at, because there was a there was a p-value for the time variable, which I believe that was the right one to look at, but I'm not 100% sure. And then afterwards, I was trying to look on the internet, but I didn't find the answer for that. So did you have the answer?
Yes, yes, you were right. We should evaluate the p-value of the time. So we use the degree of freedom, the f value, and the p-value of time to understand if time, the repeated measures, are different or not between groups.
Okay.
Yeah, but I will share with the students, and maybe I can send also when I will share this presentation, the link of a website that explains it in detail, and it's so easy to understand.
Oh, perfect, Karla. Thank you very much for this. So if we have time, we can discuss this towards the end of the presentation. Okay. Great. So I've just generated some data here just to show you if I do a plot with this data, this is going to be a straight line. So am I allowed to say that a straight line is going to be like a continuous succession or consecutive succession of points that if you actually measure those points by this line? So this is going to become the the merge among those points are going to be a straight line. This is the very basic definition of a straight line. And then If we're talking about linear regression, sorry. So if we are talking about linear regression, so this is the definition of a line. And then what is regression? What do you think is regression? Or maybe if you can give me an explanation of regression in one word, what would be your word to define regression?
Prediction.
Perfect. I like that word. I like that word because I want you to think about regression. When you think about regression, you should think of prediction. This is the, I mean, for me, this is the best word to define the regression, because regression doesn't make any sense. I mean, this is just a funny statistical word to define the prediction. What are you trying to predict? So I'm just trying to predict based on my sample, what would be the value for my population? And this is going to be the topic for today. So what you are trying to do is just to try to find a straight line that fits into the values of your sample, so you can actually extrapolate your results to your target population. And that's why I like the word prediction for regression. So that's very good. That's a very good definition. Okay, so I was here, and then I was saying that before. You remember that last week I was trying to relate the concept of t-test, ANOVA, linear regression. And I did say that all these tests are very related and you shouldn't look at them independently because they are not. And then I did explain to you that the total variance in the case of ANOVA is going to be equal, or is going to be, you can break down the total variance into two components, which are the between group variance and the within group variance. And then this is for the ANOVA, and for the special case of the repeat measured ANOVA, that within group variance is going to be further divided into two big components, which are the within subject variance and the residual variance. So in the repeat measured ANOVA, we are just interested in whether or not this within subject variance makes a difference among groups in order to make a conclusion as to whether the groups are or not different in terms of the means. But this is just for the repeat measures ANOVA. This is a special case of ANOVA, which is the repeat measures. But in general, when you are talking about ANOVA, you are talking about a total variance, between group variance, and within group variance. So this concept, I believe, is important to apply for linear regression, because as you will see, the total dispersion, you have to calculate the total dispersion of your data in linear regression. I'm talking now about linear regression, and that total dispersion can be split into two groups, which are the factorial regression and the residual, factorial dispersion and the residual dispersion. So it's exactly the same concepts, the same concepts as in ANOVA, but in linear regression, we are going to talk about the total dispersion. We can talk, I mean, you can call it total variance as well in linear regression. It depends on where you rate this, but in most papers, you are going to read the total dispersion, factorial dispersion, and residual dispersion. It's exactly the same concept as in the ANOVA. All right, any questions so far? Great. So what I'm going to do now is I'm going to try to explain to you what I mean by residual dispersion, factorial dispersion, and total dispersion. So let me just start here. Right. So do you guys have an example of linear regression or anything, any example in clinical practice? Anything we can work with this? In any other case, and it's going to be linear regression. So basically, you've got here the y-axis, and you've got here the x-axis, right? So just imagine that we are trying to compare, for example, the weight of the patient, which is a continuous variable, right? I'm going to put the weight here, and then I'm going to compare, for example, with the cholesterol levels. For example, this is just an example, and I'm just saying cholesterol or whichever the continuous variable is, because you have to compare two continuous variables. That's the theory behind the linear regression. So just imagine that you got this. And then imagine that you've got a number of patients here, which I'm going to represent here very quickly. So you got a number of patients, I don't know, maybe 20 patients, 30 patients, 100 patients are going to represent here, to be represented here. And every single point is a patient. And then same for the y-axis, because you are going to measure on the same page, in the same patient, you are going to measure the weight and the cholesterol and see if there is correlation between them. So let's imagine that there is actually a linear correlation. Imagine that there is a linear correlation. So you've got the patients, every point is the patient, and every point is the coordinate between the x level and the x value and the y value, by which I mean between the cholesterol value and the weight value. Sorry?
Comentando que ya estoy negociando otra visita con Luna. Así vamos a poder armarnos otra vez de la relación.
¿Cree que hizo algo con ella?
Guys, there's some noise in the background. Great.
Please,
So,
I'm trying to mute your microphones. Sorry for that, but it's important for the lecture.
then I'm going to keep this. And then if there's, let's imagine that there's actually a relationship between cholesterol and weight. And let me just put this in another color, for example, this one. And then there is a relation there is actually a relationship between cholesterol levels and the weight, for example, right? This is just an example. And then for this graph, you can always calculate the mean of the weight, which is the mean of the y level or the y-axis. Let's calculate this. For example, let's say this is going to be green. So let's assume that the mean is here, for example, and then I'm going to say here that this is the mean. The mean of y, the mean of the weight, okay? And then this is the mean level, okay? So if you take, for example, for a random patient, I'm going to take, let me just put in this color. I'm going to, for example, I'm going to talk about this patient, okay? Specifically for this patient. So there is a value for the cholesterol and there is a value for the weight. Sorry for my drawing. There is a value for the cholesterol and there is a value for the weight. So what you can see here, is the distance between the observed value or the theoretical value and the expected value, which is the prediction or the regression, the line regression. This is the regression of the for this particular example, which means that if we are having a good correlation, so we are allowed to draw a line here, which is what we are going to discuss with you today. And then based on this, you can actually extrapolate your data and say that for this patient, the X value is going to be this because this is my model. So I was mentioning that this is this point of the straight line, which is the prediction of your value, which value of the weights. The difference between the observed value and the theoretical value is going to be called residual variance. I'm going to put it here. Okay. So this is going to be the residual variance or the residual dispersion, because I like the word residual dispersion because otherwise you might be confused with the ANOVA. Okay, so this is the residual dispersion. And then the distance between the theoretical value, the fit value, which is this one, okay, or the predicted value, and the mean, which is here. This is going to be another type of dispersion, which is called factorial dispersion. This is the factorial dispersion, okay? And then finally, if you merge the residual dispersion and the factorial dispersion, like this, okay? So can you tell me what dispersion is it?
Total.
So this is going to be called the total dispersion. This is the total dispersion of your data, okay? So you see that the concept is exactly the same. The concept is exactly the same as the within group variance, between group variance, and the total variance. That's why I really emphasized last week that the ANOVA has a lot of things in common with t-test, and has a lot of things in common with the linear regression. And provided that you understand the linear regression, you will be able to understand the other models of regression, including the Cox regression, logistic regression, multinomial regression, and Poisson regression. But this is the very, very first step to understand what we are talking about, okay? And then I just wanted to tell you as well, because it's important for you to understand that there is an alpha value and a beta value. Let me just put in here.
Wilson,
Yes.
I guess Sobha would like to ask you a question. Sobha, please, welcome.
Yes, Soha.
I'm sorry, can you just repeat, Wilson, the residual dispersion and factorial dispersion?
Absolutely, Soha. So look, I'm going to be back here. So look, we got a sample here, which is a random sample from your population, and these data are completely independent from each other. And then, based on your on the dispersion of the shape of your data, you can actually draw a line, but sometimes you can't, because you can't see any relationship. Provided that you see a relationship, so the regression model is going to draw a line for you. And the reason for drawing this line is to determine what the theoretical values would be if a particular patient in the population had this cholesterol level. What would be the theoretical weight for that patient? I know this is a very basic example. There's lots of examples in clinical research, but I just wanted to make it as simple as possible. So what we are going to see today is how to draw this line, because this is the linear regression, the linear prediction. I'm going to predict based on my sample what would be the theoretical value for my target population, for my population, yeah? And because I draw this line, which is here, this is a brown line here. So I've got, for example, this patient, but you have to do this, you don't have to do this, STATA is going to do this for you, but for every single patient, I'm just taking this as an example, but for every single patient, STATA is going to calculate for you the residual dispersion, the factorial dispersion, and the total dispersion. Your sample for your clinical trial. And then if you got this patient has a specific X value, a specific cholesterol level, and then these patients here, yeah, this is the theoretical value. And then the difference between this and this, and in other words, the distance between the theoretical value and the observed value is going to be the residual dispersion, okay? And now, on the other hand, because you already calculate the mean of the weight, which is this line, so you can also calculate the difference or the distance between the the theoretical value and the mean of the weight, and this is going to be the factorial dispersion, and then the sum of the residual plus the factorial dispersion is going to be the total dispersion, in the same way that the within group variance and the between group variance is going to equal the total variance. Is it more clear for you?
Wilson.
Yeah, yes, Wilson. It's clear, but I just want to, in one sentence, ask, is the residual dispersion equal to the within group and the factorial equal to between group?
No, no, because I'm just trying to make an analogy between ANOVA and linear regression. The concept is the same, but the names are slightly different.
Okay, okay, that's what I want.
Okay, yes. And then
just to
sure.
Ask you, these values are important because STATA, the statistical test, will use these to calculate if there is or there isn't a linear prediction between the outcome and our independent variable, right?
So the understanding of these concepts, obviously, I mean, I'm not sure if you really need to understand this, but if you are really interested in the ANOVA, sorry, in the linear regression outputs, you really need to understand this. But in the end of the presentation, I'm going to show you which values you should look at in the linear regression output. But it's just that I always think that it's always useful to know what STATA is doing for us. It's not mandatory to know this, but I really think that this is really helpful to understand the regression models. And this is what I'm trying to explain to you. And but having said that, I don't think you should really understand these concepts in order to interpret the linear regression outputs, because as you are going to see, all you need to see is the again the R value, the R square value, which is the coefficient of determination, and the other value you have to look at is the beta value. But don't worry about that, because I'm going to cover this with a real example in STATA, so you will understand this better. So yeah, that's that. I mean, you don't really need to know that, but I really think that it's interesting to know this.
Thank you, Wilson.
So the last thing I wanted to show you, and I'm going to insert here something. So you will see an alpha value in your data, in your output, and you will see a beta value. And this is really important to understand for you. I mean, if I say that this is not mandatory to understand, this is really important to understand what the alpha value and the beta value is. Okay. So the alpha value is going to be the value of x, the value of y, sorry, the value of y when x takes a zero value, because there is a zero here, for example. There is a zero here. All right. There is a zero, but this is a theoretical zero, because you can really have a zero cholesterol level, 0 milligrams per deciliter. But in order to build your linear regression model, you have to know what the value is for this, for zero. But as I say, obviously this is going to be sorry, I'm just going to try to put this here for you to understand. This is going to be just a theoretical value, but it's important for you to understand, right? And so I was mentioning that the alpha value is the value that takes y, or in other words, the value that takes the weight when when the cholesterol takes the zero. This is a theoretical one. And then you will see here that this is the alpha value. This distance is going to be the alpha value, okay? So I'm going to put the alpha here, keep the notations. And then this is the alpha value, which is this short distance. I'm hoping you understand the alpha value. And then for every single change, let me just change the color here. For every single change of the unit, whatever the unit is for the cholesterol, in this case, for every single change of in milligrams or of deciliter, you are going to find out what the beta value is. Okay, I'm not going to do all of this, but I'm just going to explain to you what the beta value is. For example, for this patient, sorry, for this value, which is a very low cholesterol, the beta value is going to be this one. Okay, and then therefore for the next value, the beta value is going to be the slope of the straight line. So you see, this is the beta value, and this is the beta value, and so on. Okay. I'm going to keep this. So therefore, the beta value is going to be like here. Sorry. The beta value is going to be exactly that one for every single measure, okay? And then finally, the definition, the statistical definition for a straight line, and therefore for the statistical definition for a model of linear regression is going to be what? Is going to be the alpha value, sorry, the y value. The y value is going to be equal to the alpha value. Going to be equal to the alpha value plus the beta value, whatever the beta value is. Answer question. Whatever the beta value is, yeah, multiply by the x value. And this is the definition of the statistical definition of linear regression. And this is something that you have to understand, because if you don't understand this, you won't be able to understand survival data, Cox regression, and everything else. So this is really important to understand what the beta value in your output is and what the alpha value in your output is.
Wilson,
Yes.
Sobha asked if this alpha and beta value is related with type 1 and type 2 error. Sobha, it's not related. It's alpha and beta concepts for linear regression, right? There is no relation with type 1 and type 2 error that we learned weeks ago.
Okay, I've become much more sophisticated now. Thank you.
Yeah, yeah.
But that was a good question, Shobha, because actually there might be a confusion with the alpha value, beta value. But yeah, you're right, Karla. You're right. This is completely unrelated. Completely unrelated. Okay.
Wilson, just to try to translate this equation for words, not only beta and alpha, maybe alpha would be our first value in our linear equation, and beta will be the modification in weight based on our cholesterol level. For example, if we changing 1 or 2 the cholesterol level, this beta value will change our outcome in that value, the beta value, correct?
Correct. Exactly. Yes. But also you have to understand the outputs as well, because this is like a random example, but just imagine that the beta value is, for example, the beta value is 2, for example. So that my interpretation for the beta value for my model is that for every single increase in milligrams per deciliter of cholesterol, for every single increase, if the beta value is 2, so my weight is going to increase 2 kilos, which usually doesn't make any sense. And that's why usually you have to, in clinical research, you have to dichotomize your variable or categorize your variable in order to interpret this beta value easily.
So can I ask you a question?
Yes,
the beta value is actually very important. So you, even if you don't have the values on your table, you can infer, like in the future. I mean, and I know this is not like the future, but the beta value is important if you want to know more, like what's happening beyond your graphic. That would be that.
You are right, Flavia, because remember that I'm comparing the beta value with the theoretical, not with the observed. This is the theoretical. This is the distance with the theoretical. This is just the theoretical, not observed, which means that you might have missing data here, but you are just comparing with your line. And that's why it's so important to draw the line, because if you don't have a line for regression, so you can predict your value based on the beta, on the beta value.
And that's why linear regression is the most important test when you want to predict something. It's better to use linear regression, right? Because of this beta value.
Because of this beta value, but remember that the linear regression is only used when the independent variable is continuous and when the dependent variable is continuous as well. If the dependent variable is dichotomic, immediately this is going to be logistic regression, as I explained to you in my concept map in the first slide I showed you.
Wilson, sorry, but would you mind repeating alpha and beta? The definition.
Yes, Daniela. So the alpha value is going to be the value of Y when the cholesterol or the X value is equal to 0. So the alpha value is going to be exactly this point. Why? Because when cholesterol is 0, obviously it's not 0, but this, you have to do this in order to understand, and STATA is going to do this. It makes no sense because no patient is going to have 0 cholesterol level, but because you will always have a beta value in your output, you have to understand why the alpha value doesn't make any sense at all. So you shouldn't look at the alpha value, because the alpha value is the value that this, in the hypothetical case that the patient had 0 cholesterol level, the weight that the patient would have. So because it makes no sense, but you will always see the alpha value in your regression output, whatever the regression is. Cox regression, linear regression, multinomial regression, logistic regression, Poisson regression, you will always come across with this alpha value. And then I'm just doing this in order to demonstrate to you that the alpha value doesn't make any sense and you shouldn't look at. The one you should look at, and you are really interested, is in the beta value. Because the beta value is the change for every single unit, whatever the unit is, in this case, it is going to be milligrams per deciliter. So for every single change in the unit of the cholesterol, my population, because I'm talking about the population, not the sample anymore, is going to have a predicted weight based on my regression model.
Okay, thank you.
Okay, good. Great. So I think I'm done with this part. And then I just wanted to, I don't know, what is this? Why you did this?
Wilson, I'm
Yes.
so sorry. My internet is not good. I need to log off and try to log in again. I know that it will, I will try to change my internet now. Maybe if you can wait some minutes, please.
So in which case, can we have a break of 3 minutes and then we can come back in 3 minutes?
Great. Thank you.
Perfect. Good. Can you guys hear me?
Yes, we can, Wilson.
Perfect. So, because this is really important for you, and I don't know if you have any questions or anyone hasn't understand. I'm very happy to repeat this, but I really believe that this is important for you to understand. As I say, the alpha value and the beta value are really important in regression. Okay, so what I just did in my slide is exactly this. Okay, so so you got here, as I explained to you, the mean of the y variable in that case was the weight, and you can also calculate obviously the mean for the cholesterol levels. And then what I just done was just to calculate the distance. Sorry, this is not the right slide. Let me see another better slide.
Wilson,
yes.
Amir asked a great question. If there is negative values for beta value, I guess that is, we can have negative beta value in linear regression, right?
Yes, you can have a beta value negative, which means that the relationship is not positive, but negative. That the more the y value is, the less the x value is.
I guess a great example is creatinine clearance and age, for example.
And age, the more the age, the less the creatinine clearance, in which case you will have a beta value negative.
Yes.
Great question. Okay, so this is what I've just done here, but I just wanted for you to understand my slide. But this is another way to present to you the same concept. So this is my definition, my statistical definition for a straight line, as I explained to you, and then the alpha value is going to be this distance, as I just explained to you. And then for a single patient, for every single patient, STATA is going to calculate this, because I've got a predicted line here, so you can always calculate the distance between the observed value and the theoretical value, which is going to be the residual dispersion. You can always call the residual variance, but I like to say dispersion because sometimes my cause a confusion with the analysis of variance. And the distance between the theoretical value and the mean of the y, of the weight in this case, is going to be the factorial dispersion. And you just need to square this in order to calculate your dispersion. So this is y observed minus the y theoretical. and this is the y theoretical minus the y mean, the mean of the y, and then you square those values, obviously the sum of all these values, you are going to have a value for residual dispersion, and then you sum this, you sum up this residual dispersion with the factor dispersion, is going to be equal to the total dispersion. Now, why do you think we are squaring these values? I don't know if you can understand this. Why do you need to square this?
So that we don't have negative values.
That's a good reason. That's a good reason. That was Flavia, I think.
No, it was Paula.
Sorry?
Paula.
Thank you, Paula. That's a very good reason, because otherwise you're going to have negative values. But the other reason is because if you don't square, let's assume that you are just summing the difference, because this is the summatory. This is not this is only for one patient, but imagine that you've got 3,000 patients. So for every single patient, STATA is going to do this and calculate the summatory of this. So if you sum this, let me just put here. Let's see, there are other points here. And then you're just trying to sum this with this for every single patient in your sample, yeah? This distance, yeah? And so on. So mathematically, if you sum this one with this one, with this one, and this one, and so on with this one and this one, and for the total sample, you are going to have a value which is always 0. So you are not going to have any residual dispersion, any factorial dispersion, or total dispersion, because the sum of this plus this plus this plus this and the total sample size is going to be always 0. So this is why this is a way to avoid that the sum is equal to 0. If you square this, you are going to measure actually the dispersion by squaring the values. And this is the main reason for the squaring, because otherwise you will have a 0 always, whatever the sample size is. No matter if the sample size is 10 or 3,000, your result is going to be always 0 for mathematical reasons. And I'm just trying to explain to you why. Okay? So in regard to the assumptions for a linear regression, we are going to talk about this as well, because they are very similar to the ones we discussed with the parametric test. But the first assumption is that there is linearity. There is a linear relationship, because if they are not relationship in your data, linear relationship, there's absolutely no reason to run a regression model. And this is the end of your study. If there's no linearity, there's absolutely no reason. So you really need to test whether your sample has a linear relationship, because there might be another types of relationship, but it has to be a linear relationship. And this is the first assumption. And then the second assumption is that these data are completely independent each other. Yeah, so we are not doing any repeat measures, for example, for this value and this value. And then the other one is the homoscedasticity of the residuals, which are these values. The residuals are the difference between the observed and the theoretical values. So those values must be homoscedastic, must have equality of variances, as we discussed a couple of weeks before. And then the last assumption is that the Y value has a normal distribution. Okay.
Wilson?
Yes.
Do you have a perfect linear assumption
You will never see in clinical research this, never ever. And the reason is because you're dealing with biological values and you are dealing with random samples. So you will never ever see a perfect relationship because this is biology. So there is always a degree of uncertainty. One patient might be here and here and here and here. So what we are trying to do is just construct or build a straight line in order to make an extrapolation of our data to our target population. But obviously you will never ever see this. And if you see this, there's absolutely no point to run a linear regression model because you already know what the values are. So what the reason is for your regression model.
Wilson, also Melissa make a great comment on chat regarding your comment that if we do not square, we would have a zero value for the math, the calculation. But she answered that maybe in real life science, it's possible to have to not to have a zero value because as you brilliantly explained, linear regression has some assumptions, but in real life we do have some outliers, we do have some kind of not perfect, almost statisticity. So in real life, maybe I know that the statistician, they plan the counts and all the mathematical plan to have a perfect calculation. But in real life, maybe if we sum this value, we won't have a zero value. No? What do you think? And Melissa, I don't know if it is your comment. Please, if you want to open your mic and comment.
Yes, I think that's a great comment. But this is a mathematical equation, and I do believe that even when there's lots of variability, because you are constructing this line, so in theory, and this is a mathematical concept, the sum, because I mean, you are right in saying that obviously there's lots of variability in your data. There's also lots of variance and lots of outliers. But from the mathematical point of view, because you are constructing an artificial, this is artificial line, a theoretical line. So that theoretical line is not more than theoretical. And because this theoretical, and because of mathematical reasons, the difference with the theoretical value is going to, the sum of the difference with the theoretical value is going to be always zero.
Okay, because the line was constructed based on this value, right? So in that way, the count will be exactly zero.
Exactly zero, exactly zero. And I can demonstrate to you. Let me just, I'm going to drop this because this is a great question actually.
Because just to explain more my concern, because if I had a big outlier for one side, for example, maybe I won't have this another outlier from the other side. But I understand that the outlier from above, for example, will get the line closer for this value, right? That's the why in general linear regression does not accept a lot of outliers.
Yes, it doesn't accept a lot of outliers. Let me just do something here. I've got a sample here which makes no sense, but I just wanted to show you a little bit this. Let me see. Okay, let me just not to make so complicated this. So this is, for example, you got a value which is 1, 2, 3, 4, and 5. Okay. So you got what is the mean of this value? So of this variable, so it's going to be 1 plus 2, 3 plus 3, 6 plus 4, 10 plus 5, 15. And 15 divided by 5 is going to be equal to 3, right? I'm going to demonstrate this here. So you got 5 values, 5 observations. There is a mean here, and there is a minimum and maximum. So if I sum this, it's going to be equal to what? To 1 minus the mean, which is 3, plus the next value, which is 2 in my sample, because you can see here, 2 in my sample, 3, 4, and 5, but it could be whatever. So 2 minus 3, because 3 is the mean of my sample, plus 3 minus 3, plus 4 minus 3, plus 5 minus 3, right? And I'm not, I'm sorry. 5 minus 3. And I'm not squaring, obviously, because I just wanted to show you. So that would be the calculation for the sum of the sum of the difference without squaring. So 1 minus 3 is equal to minus 2, and then minus 2 plus 2 minus 3 is equal to minus 1, and this is going to be plus 3 minus 3 is equal to 0, and this is going to be plus 4 minus 3 is equal to 1, and then 5 minus 3 is equal to 2, right? So minus 2 plus 2 equal to 0, minus 1 plus 1 equals to 0, and then my value is going to be 0. Do you understand why?
Yes, thank you so much, Wilson. Yeah, I absolutely understand now. But I thought regarding the real life, but even in real life, if I run the linear regression, it will give me the outlier will elevate the line.
Always.
Closer than this value. Even in equation that's not valid, because we know that outliers can invalidate your equation, but based on this equation, all the value will be 0. Thank you so much.
Okay, great. So yeah, that was a great equation actually. So that's the reason we have to square this, all right? So I think I'm done with this, and then I'm going to go through something slightly more complex. I'm going to be as slow as I can, but we have to make some progress. I don't know what do you think about this. So basically, this is what the STATA does for you. So the methodology for constructing the straight line is called the least square estimation. And why is it called this least square estimation? Because STATA is going to try to find a line for which every single value is the less distance, is the nearest value to the theoretical value. So this is why it's called least squares. I explained to you why we need to square, and estimation, because this is going to be a theoretical line. And this is the explanation as of how STATA calculate the lines for us. You don't need to understand this, but you are really interested in this, in the calculation of the STATA behind the output. This is the explanation. So it's basically you've got 12 patients. It's not really hard to understand this because you've got, let me just put a pen here. You got 12 patients, only 12 patients, because otherwise it's going to be a nightmare to calculate this. I mean, you can imagine if you have 3,000 patients, but then you got an X value for everyone, whatever the value is. It must be a continuous value. And then the observed or experimental value for Y, which is this one. And then your question is whether or not these values are correlated. They might or might not be correlated, and this is your research question. In order to do this, you have to multiply the X times Y. For example, 22 times 4 is 88. And then you have to come up with the theoretical Y. I did explain to you how to calculate the theoretical, but I'm going to explain to you later on more. And then calculate the difference of each value, which is, for example, for the X value, for example, you got a mean of 17. And for the Y value, you got another mean, which is not written here because it's not important. But what I'm trying to say is that you have to put, you have to break every single patient and then calculate the difference. And then once this difference is calculated, for example, in this case is 22 minus 17. So it's going to be here, the difference here, yes? And then you have to square this because as someone said, this is going to be positive, always positive. You see that I've got a lot of negative values here, but once you square everything, this is going to be positive, and then all you need to do is just sum up all this value, and then you will come up with a big value here. And based on all of this, you have to calculate the beta value, which is given by this equation, beta value. I can demonstrate this in STATA if I have time, but we'll see how it goes. But I mean, there's a beautiful demonstration in STATA as of why this is true, why the beta value needs to be calculated as it is here. And then based on my example, the beta value is going to be this one, okay? And then after this, you have to come up with the standard error of the beta value in order to calculate your 95% confidence interval. Again, you don't really need to understand this, but I think it's more important for you guys to understand what the 95% value is. Right? So the 95% value comes from the beta value plus or minus the t value, and the t value you might remember from last week that you have to look at the t table for n-2 degrees of difference because my sample size is 12. So you have to go to the internet and look at the t value for 10 degrees of difference because it's n-2. And by the way, the degrees of difference in linear regression is always n-2. And then this value is going to be multiplied by the standard deviation of the beta, which can be calculated here. And then, as I say, if I had time, I can demonstrate to you in a STATA example why this is like this. And then eventually you are going to come up with a confidence interval here, which is important to understand your output. So as you can see here, I've just made the same example in STATA. So you can see here the beta value is 0.4856. And then this is going to be exactly the same beta value here, 0.4856. And I calculated the 95% confidence interval for that beta values, which is between 0.3011 and 0.659, which is exactly this one, 0.311 and 0.659. I'm going to spend a few minutes to explain to you every single value here, because it's important for you to understand as well what every single value gives. Because, I mean, as I said, the alpha value is not really important in clinical research. And by the way, the alpha value is given by this. In the outputs of STATA, the alpha value is the const for the constant. There is a constant here, which is the alpha value, and the beta value is this one. But I'm going to explain to you every single value, and hopefully you will understand everything in linear regression. Because as I say, it's important because the layout of the output for linear regression is exactly the same for logistic regression of whatever the regression is. So that's why it's really important to understand all these values, okay? And that this is the explanation. Yes.
Wilson, Amir asked us a question. If there is a true 0 for alpha value example in health science. I was thinking about maybe weight and age in days regarding newborns, for example, age 0. This is alpha value, and we'll have an age, and 1 day and 2 days old and 3 days old will change the beta value in some grams in weight. I don't know if it's a true alpha value of 0 in this case.
It might be true, depending on your data set, obviously, but the most important thing for you guys to understand is that the alpha value means nothing in the regression model, nothing. You have to look at the beta value. We never ever we don't even look at the alpha value or whatever the. You can see here, this is the beta value and this is the alpha value. We never ever see this, we never interpret this in clinical research. I haven't seen anyone interpreting the alpha value. So please forget this, all this line, don't be confused, because we never interpret that one. It has no interpretation in clinical, in the clinical context. What you really need to look at is at the beta value, which is this one, the standard error, which is this one, yeah? And the standard error is very important, because based on the standard error, as I just explained to you, STATA is going to calculate 95% of confidence interval. But please disregard this, because I have never ever seen an interpretation in clinical research for that output, for alpha.
Thank you, Wilson.
Mm-hmm. Right. So this is my explanation for how STATA does the line, which is a little bit complex. And this is my explanation for the Pearson coefficient. But as I say, I'm not really going to explain to you this because otherwise it's going to be a very long presentation. But what you really need to understand is that when the assumptions are met, these assumptions for linear regression, when these assumptions are true, you are allowed to use the Pearson coefficient. And we are going to have a real life example in my STATA in order for you to understand how to run the Pearson's coefficient. But if your data is not parametric, if your data has not normality, homoscedasticity, so you have to run linear regression with interpretation of the non-parametric test. In which case, what is the non-parametric test for linear regression? If the parametric test is Pearson, what is the non-parametric version?
Spearman.
Spearman, exactly. Spearman. So let me see if I have here the Spearman. So this is the Spearman RHO rank correlation. Let me just make a little parenthesis on this. Do you really understand why is it called RHO? Does anyone have any idea what that means? RHO for Spearman?
HO would be no hypothesis.
That's a good guess, Karla. Any more thoughts? Any thoughts? I'm going to change the question. My question: Do you know why the chi squared is called chi square? What do you mean by chi? CHI.
Those are Greek letters.
Perfect. Who was that?
Dante.
Dante, thank you for that. Let me see if I have. So in statistics, we use a lot of Greek alphabet. I don't know if you know that, but the Greek alphabet has got 24 letters, as you can see here. Obviously, most of them are going to be used. Exactly 12 of them, in my knowledge, are used in statistical the statistical concepts. So what you can see here is the whole alphabet, the Greek alphabet, and then you can see here the interpretation for some of the Greek letters that we usually use in statistics. For example, the alpha and beta value the alpha is going to be the significant level, as you all know by this stage. The beta value is going to be the possibility of type 2 error. And then I might need to modify this slide because the alpha value is also has also an interpretation which is completely different in the concept, in the context of linear regression. So this is the alpha value and beta value we just explained to you. And then there is another one, which is the delta value, which we use it for non-inferiority margin in non-inferiority trials and equivalence margin. And then there's another one, which is the epsilon. We didn't discuss this because it's a little bit more complicated. And this is one of the assumptions of the repeat measure ANOVA. Basically, the sphericity, this is a concept that has absolutely no sense, but the definition for the sphericity is the homogeneity of variances within the subjects, within the time variance, within the time variable. This is the sphericity we usually see in repeat measures ANOVA. This is one of the assumptions you have to test for repeat measures ANOVA. Unfortunately, this is a very special case and it's a little bit complex, but I just wanted to point out that. And there's another one, which is the kappa for concordance coefficient. You can see here more of them. But then this is the RHO, and this is the name of the P letter for the Spearman correlation coefficient. And then you got some more examples. Today we are going to talk about the tau, Kendall tau. So tau actually is the name of this letter, of the Greek letter. So as you can see today, we are going to talk about the RHO Spearman test and the tau Kendall test. And this is the reason for that. And then my question regarding the chi is called chi squared because the X letter in the Greek alphabet is chi. Actually, this is the name of the letter. That's it. Okay, sorry for the parentheses. And I was going to explain to you here the Spearman. So this is the Spearman RHO rank correlation. So basically, I've got the same data set for Pearson, but just imagine that you got no assumptions of normality, no assumptions of homoscedasticity. So you have to come up with this. So the calculation is actually a lot easier because the equation is a lot easier to calculate. And you just need to, as always, rank. You always, and we can emphasize enough that the ranks are always related to the non-parametric tests. Yeah. For example, let me see, for example, look at this. So obviously, I don't need you to understand the equation, but look at the non-parametric test. This is always rank, non-parametric rank, and non-parametric Wilcoxon rank again, and non-parametric for repeat measures ANOVA rank. And this is the reason that non-parametric tests have much less power than the parametric ones. And for the Spearman, this is not the exception because you've got a rank here, a rank here, a rank here. So you always calculate the non-parametric test with the ranks, right? So you just calculate the ranks for X, calculate the ranks for Y, and then calculate the difference, and then square the difference, and then based on this equation, you will come up with a number here. And then the interpretation, by the way, of the R for Pearson, RHO for Spearman is exactly the same, which means that 91% of the data are explained by the difference, which means that there is a very good correlation between, there is an excellent correlation actually between those variables, because I made it in purpose that this is actually correlated, because as you can see here, these are not the same numbers, but they follow the same trends. So this is why my calculation is very good. Again, you won't see this very often in clinical research because as we discussed last week, a good correlation might be anything more than 80%. That would be a good correlation. Between 60 and 80, that would be acceptable, and less than 60 is definitely not a good correlation. So based on this number, which is 0.91, you just need to go through the internet and look at the t-square if the if the sample size is more than 10, which is my case, and then just compare the values given by the table. In this case was 0.91, which is here. 0.91 is something like here. So it's completely out of the null hypothesis, in which case I'm going to reject my null hypothesis. I'm going to say in my paper that we found very good correlation between X and Y, and which has been statistically significant. This is a Spearman correlation, right? And then the Kendall tau is different because you have to deal with ordinal data, right? With ordinal data. So again, it's the same example. It's the same example, but the research question is different, but because you are not interested in knowing where these values are correlated. In Kendall tau, you are just interested in these ranks in a longitudinal way are correlated, but the ranks, not the values. So you see that the research question is different because if you have ordinal data, so you might be interested in know where the ranks are correlated between X and Y. I know it's a little bit hard to understand this, but there is a big difference between the Spearman and the Kendall tau. And what I'm trying to say is that despite that this is exactly the same data set, the difference is your research question. What you are interested in? Are you interested in looking at the relationship between this? Or are you interested in the trends of the ranks? Yeah. So based on this, you are going to calculate the concordant pairs here. Here, I can explain to you in depth how to calculate the concordant pairs, but unfortunately, we have no enough time to discuss this. And then the tau test is given by the concordant values minus the discordant values over the concordant values plus the discordant values. I'm going to give you an example of the Kendall's rank that I just came to my mind a couple of days ago. So imagine that we are doing our research project, which is true, and we got 12 research questions for our project instead of patients. So we got 12 research questions. Just imagine that, yeah? And then based on the rank of the students, for example, just imagine that for the students, the rank was, this was the first one, the second was the third, and so on. And then just imagine that for the TAs, the rank was different. For example, for the students, the second research question was the second. And for us as a TAs, that research question was the first in the rank. And then you follow the ranks, you might be interested in whether or not those ranks are correlated, but the ranks, not the values, yeah? So if that's my research question, if there is concordance between students and TAs regarding the rank of the research question for our research project, if this is my research question, I'm allowed to use a Kendall test in order to prove whether or not these trends are significantly different, right? So in this case, I calculated, and then it was 0.72, which was fair concordance between students and TAs. I don't know if you can understand my example.
Yes, I guess it's a great example because the students just ranked the research question to try to find the best one. And if we planned a TA rank, we could compare both. I guess it's a great example. Wilson, I guess Camila asked you to help us to interpret the confidence interval, because you shared with us the example of linear regression and the beta value with confidence interval, and how we interpret the confidence interval of beta value and the p-value, also the equation.
Right. So excellent question. I'm going to propose you something. I'm going to build some a data set for you. I don't have any data set, but I'm going to do something for you now. And then meanwhile, you can have a second break. That would be great. So you can give me 3 minutes to make up some data set for you. So shall we have a 3 minutes break?
Yeah, I agree.
Perfect.
Thank you.
Can you guys hear me?
Yes, Wilson, we can.
Perfect. So this is the last part of my presentation. Hopefully it's going to take me no more than, shall we say, 40 minutes. Let me see where we are here. So I'm just going to discuss with you this. So this is what I believe is a good example of linear regression, correlation, how to understand this in our STATA output. And this is going to be the most important part of my presentation, because I'm going to explain to you how it works in this data. So I'm going to explain to you every single number of the output, okay? So my idea, unless you have a different idea, I mean, I'm always happy to change a little bit my data. I don't have any data set, by the way, so I have to come up with some numbers and some random numbers. But unless you have a better idea, we can work on this, which is the potential correlation between the maternal blood sugar and the birth weight in obviously in pregnant people. What do you think about this? Do you think it's a good idea to work on this, or do you have another idea to work on the two continuous variables to see whether or not there are correlation between them?
Maybe, Wilson, here we should reflect about the clinical relevance, right? To understand.
Yes, that's why this is a very, very, very important example. So let's go for this then, okay? It's going to take me, unfortunately, it's going to take me some time. Let me just drop this. I don't need this anymore. And it's going to take me maybe 3 to 4 minutes to do a nice data set. So please bear with me. 3 minutes, please, okay? Guys, almost there, okay?
Great, Wilson. Take your time. It will be amazing to have a example, a real example.
Yeah. Guys, almost there, okay? Thank you for your patience.
Wilson, what is the second variable, the second column?
I'll just finish with this show up and I will explain to you what I'm trying to do, okay? So let me just rename the variables. Rename variable one, variable two. And then let's say I'm going to call a variable which is called MBS, sorry. And then the other one is going to be bear weights. Okay, let me just, sorry, it took me longer than I thought, but I'm done, sorry. So based on my proposal, I'm just going to try to compare sample size. I've got 50 patients, and for 50 pregnant patients, and for every single patient, measure the maternal blood sugar, which is here. So this is the maternal blood sugar. And then I'm just trying to see whether or not the birth weight is correlated to the maternal blood sugar. Obviously, if you can see my data set, I've just generated 50 patients, and on purpose, I designed a sample for with a very good correlation. For example, for this patient, the blood sugar was 263, and therefore the weight was really high. And for this patient, for example, for my first patient, the blood sugar was 56 and the birth weight was completely normal. Obviously, you don't need to organize this in ascending order. I just generated this in order to explain to you some important bits, but your data is completely unorganized, and which is okay for STATA. So you just need to bring the data here and that's it, okay? Right, so based on what we've learned today, what would be the y variable and what would be the x variable? If I trying to explain to you, well, I'm trying to see what the difference is between the maternal blood sugar and the birth weight. So what would be the y variable or the dependent variable, and what would be on the other side of the equation?
The dependent is the birth weight.
Yes, the dependent is the birth weight, because I'm trying to address my research question whether or not the birth weight is explained by the maternal blood sugar, not the other way. No, I'm not trying to find out where the maternal blood sugar is explained by the birth weight, because biologically, the birth weight must be explained by the, and at least that this is my theory, this is my null hypothesis, or this is my research question, right? So because the dependent variable is going to be birth weight, is going to be right here. So birth weight. And sorry, before doing this, the first step you have to do this, you just need to graph your data to see what the data looks like. And the way to graph your data is with the command scatter, as you can see here, scatter, okay? So scatter what? Scatter the y and the x. So the y, we say that is the birth weight, and the x is going to be, therefore, the maternal blood pressure. So let's see what happens. So you see, at first, I can see a very good correlation, obviously because I made it in purpose, but I just wanted to show you this. So according to my data set, apparently there is a good correlation, but this is just the first step. I just need to demonstrate whether or not there is a correlation between maternal blood sugar and the birth weight. Apparently yes, but then the next thing you have to do is to run a Pearson correlation. Before drawing any regression model, you have to really find out if there is a correlation. If the Pearson correlation is negative, when I say negative, is non-significant. If the Pearson correlation is not significant, so we can't really build any linear regression model. And then in which case you just need to categorize your data or transform your data in order to make it linear if possible. Sometimes it's not possible at all. So the comment for the Pearson correlation is called in STATA a pair. The Pearson is called pairwise correlation. This is what is called in STATA the Pearson. And the comment for this, because it's called pairwise correlation, so the comment for this is PY core. Okay, P for pair, W for wise, and core for correlation. And then PY core what? PY core, my Y variable first, as I say, always the dependent variable first. So the Y variable is going to be birth weight, and then the X variable is going to be maternal blood pressure, okay? I'm going to run this. And then actually there is a very good correlation, is 88.2. I did explain to you that more than 80% is an excellent correlation, so good news. We can run a regression model. But before this, is it significant or is not significant, that 0.88? Is it statistically significant? Is it statistically good, a good model, a good correlation, sorry?
Wilson, I guess for correlation, we use the cutoff more than 80, 0.5 to 0.8, to very good, good, not so good correlation. We use p-value also in correlation or not?
We do, yes. We do.
But where is p-value?
So the p-value is going to appear here. You type here, I'm going to run exactly the same command. And then if I put a comma here and I put that sig for significance, you're going to have a p-value immediately below this. Okay? So the p-value, because it's so good, my model, you saw my model is very good. So the p-value, can you tell me what the p-value is? Can anyone tell me what the p-value is?
0.000.
That was a tricky question, because when you are reporting your results, you shouldn't really, I mean, let's do something. For example, you are writing your paper, and then I could say, for example, we have found statistically significant.
We can say that it is less than 0.01.
That's my point. Yeah.
0.00.
So we have found a statistically significant correlation between birth weights and maternal blood pressure. Yeah. Imagine that you are writing your paper, and then you just need to inform this why this is significant, because my R for Pearson was equal to 0.8820, and then my p-value, and this is my question. Guys, your p-value, you should never report a p-value at 0. Why? Because 0 in statistics, we always have a level of uncertainty. Otherwise, this is not a statistical anymore, and this is, I mean, there is always a level of uncertainty, and that's why we have to report the intervals, the confidence intervals, right? So you shouldn't never say like p equal to 0.000, because it's not really 0.000, and STATA is rounding this value. Because it's only 4 integers here, so it should never be 0.00. It should be less than point something like this, and this is what you should report into. Oh, sorry, this is less than 0.0001, and this is the right way to interpret 0.000 p-value, right? So obviously, because my model is so good, so it's very significant. So I'm not surprised, because it's 0.88, and this is the way you have to run the Pearson. Okay, and then because we got a linear relationship, assuming that we got all the assumptions for the regression, so you can actually, after looking at the data visually, and after testing for correlation with Pearson and having a p-value. So you, at this point, you are allowed to draw regression model, to run a regression model, a linear regression model. And
just a quick question. Also, Amir asked a great question regarding, as you said, we must follow all the assumptions. And normality of residuals is an important assumption for linear regression. How should we test this normality? Because it's a little bit tricky, because it's not normality of our data, but it's normality of the residuals of our data. So could you try to explain us how to test?
I will explain to you very, very easily how to calculate this. I don't know if the time is going to allow me to explain all these things, but it's really important for you to understand, because this is a special case, and there are special commands to run the residual normality. This is nothing about, it has nothing to do with normality and homoceasticity we talked about a couple of weeks ago. I mean, the definition is the same, but the way to do this in STATA is more complicated, but let me show you how to do this. So the first thing you need to do is just run your regression model. And again, you don't need to type regression, just rec for regression. And then the syntax is, again, is regression y and x, okay? Regression y, x, that's very easy, pretty easy. So, so what is the y again? So my y variable is, again, the weight, and then my x variable is therefore the other variable, okay? Let's see what happens. Great, so this is the tricky part, because we've got regression model here. And then my job for the next 5 to 10 minutes is to explain to you every single number of this, okay? But before doing this, can anyone explain to me what the beta value is here? Obviously, I can see that the beta value is 5.81, but can you interpret this beta value, or can you report this in your paper? Any ideas how to interpret the beta value?
Well, by seeing it's positive, you can see that the inclination
there is a positive relationship. That's a good conclusion. And how about the 5.81?
I would just assume that the inclination is 5.8, like it's a good inclination. I don't know.
Okay, so the trick is look at your data. Look at your data, yeah? So the birth weight is in grams, right? This is in grams, okay? And the mean blood sugar is in milligrams per deciliter, okay?
So for each unit increase of sugar, of blood glucose, you have 5 grams plus of weight, is it correct?
Exactly, so for each increase in, for each increase in 1 unit of the X, yeah, for each increase in 1 millimeter of mercury, sorry, in 1 millimeter per deciliter of blood sugar, the birth weight is going to increase 1 gram. Now, my next question to you, and that's my point, as Karla said like 20 minutes ago, is it, this is statistically significant, but is it clinically relevant to say that for every gram, the blood sugar is going to increase 5 points? I don't think it makes any sense. I don't think it makes any sense, because my interpretation for this is that for every single change of 1 gram, because of the nature of my data, for every single change of 1 gram, my blood sugar is going to increase 5.81. It doesn't make any sense.
It's the opposite, not?
Sorry, the opposite. Yes.
It's the opposite. For each 1 milligram per deciliter of glucose, it will increase the baby weight in 5.8 grams, right?
5.81 grams, exactly, Karla. That's my point. So this is not.
It's correct. It doesn't make any sense. What we as clinicians should do with this information?
So this is not interpretable. Your model is not. Your model is statistically significant, and it's a very nice model, but it's not interpretable. It's not interpretable for me. What would be the solution then? How can we do? Shall we start again the study and draw the data set and say that this is absolutely useless model because it has no clinical significance?
We should try to categorize.
Can we categorize?
For example.
Yes, exactly.
Yeah.
That's the answer. Exactly. So that's my point. Okay. So you just need to categorize. What are you going to categorize? You're going to categorize the the maternal blood sugar. Okay. And if you categorize this variable, and I'm saying that this is a continuous variable, does it remind you of any test? Remember that this is the dependent variable and this continuous, and this is going to be my categorical value. And I'm going to categorize these maybe in 3 or 4 groups.
ANOVA?
ANOVA, exactly, ANOVA. So, so this is why, and I don't know how many times I've said this in my presentation. ANOVA is another way to present exactly the same problem, but it depends on your research question as well, because here your research question is different. Your research question in regression is whether or not these data are correlated, right? And in ANOVA, we said that the research or the null hypothesis is whether or not these groups, the big weight between groups are different. Do you understand the difference in the research question? This is my point. I mean, ANOVA is related to the t-test. ANOVA is related to regression. All these tests are related, okay? But because my question is not ANOVA anymore, I'm not interested in knowing whether the airway is different between groups. I'm interested in the correlation. So that's why I'm running a linear regression rather than ANOVA, even when the F value is going to be the same, actually, as I'm going to show you, okay? So it actually depends on your research question, what to run. You need to run ANOVA, you need to run linear regression. It depends on your research question, okay? So did you remember how to categorize the variable? I'm going to do this quickly. So as I said last week, recode mean the minimal of the maternal blood sugar, but let me just create a new variable. I'm going to generate a new variable, which is going to be called maternal blood sugar categorical, something like this. And this is going to be equal to the same maternal blood sugar, okay? And then I'm going to record my new variable, which is maternal blood sugar categorical. How I'm going to record this? So I want to say maternal blood sugar. I want to say, for example, and this is just an example, minimal and 100 equal to 1, okay? And then I'm going to say that from 101 to 101 to 200 equal to 2. Okay. And then from 200, 201 till the maximum, whatever the maximum value is going to be equal to 3. Do you understand this?
Yes.
I'm making any mistake. Minimal to 100 equal to 1. 101 and 200 equal to 2, and 201 to the maximum value, whatever the maximum value is equal to 3, right? Okay. Let me see what that did for us. So this generate my categorical value, yeah. And then because this one, for example, because this one is more than 100 and less than 200 is 2. And then because this one is more than 200 is going to be 3, right? And then all you need to do is just run your regression model with your new variable. So again, your y variable is going to be var weight. This is our research question. And then now your dependent variable is not going to be MBS anymore. It's going to be MBS categorical, right? Does it make more sense, this coefficient?
Yes.
Can you tell me, Tiago, how to interpret this coefficient?
So each unit of the categorized blood, like the mother blood, will increase for like 400 grams in the outcome, in the bird weight.
Yeah.
Is that right? I don't know.
So look at my categorize, my way to categorize the variable. So the unit is not going to be milligrams per deciliter anymore. The unit is going to be 100, right? 100, because I say that less than 100 is equal to 1, 100 to 200 is equal to 2, and more than 200 is equal to 3, right? So that means that for every 100 milligrams of increasing the maternal blood sugar, the baby weight, which is our question, is going to increase by 443 grams. Does it make more sense in the clinical context?
Yes.
Perfect.
Yes.
So as you can see, I'm not talking about the alpha value. I'm not interested in this. I'm not interested because it has no meaning. Actually, the interpretation for the alpha value would be that if the maternal blood sugar was 0, which is not going to be 0, the baby weight is going to be 2,687 grams. Does it make any sense at all? Have you ever seen any patient having a maternal blood sugar of 0?
No.
No.
So this is why I say to you, don't look at the alpha value. And my job for the next few minutes is to explain to you every single value, but I just don't care about the alpha value at all. I mean, I don't care about the standard error, coefficient, t-value, p-value, 95% confidence interval. Don't be confused. I mean, the data, your data is this, okay? Don't be confused about that. And I'm hoping that by now, you can understand the alpha value.
Yes, yes, I guess we are understanding now, but I also agree with you that the alpha value is not really important, but when we want to predict and to construct or to build our equation, this alpha value will be important because it will be our baseline value. But
yes.
I agree with you, what really means clinically is the beta value, is the difference that
Exactly.
my, not intervention, but my independent variable will change my outcome.
Yes, exactly. So let me just back to my initial example here. Just imagine that this is the maternal blood sugar, and this is going to be the birth weight actually. So the alpha value is here, and then in the hypothetical case that the maternal blood sugar was 0, the weight of the baby would be, I think, was like 2,600. So as Karla said, this is important to understand that the line for the regression starts here, but you don't need to worry about this because STATA is going to do this for you, right? But I think it's very interesting to know where the alpha value came from in order to not to be confused. But as Karla said, it's important to understand this, but it has no clinical meaning at all. It has a lot of statistical meaning, yes, I agree, but what would be the clinical meaning of the alpha value? Nothing, because I will never see a patient with 0 of maternal blood sugar. Do you understand that? Great. So this is the interpretation of my beta coefficient, okay? And let me just do something here. For example, if I run an ANOVA birth weight, as you can see, it's not exactly the same, but you can run here the regression, provided that this is categorical. It should be exactly the same. Let me think. So you see here the ANOVA model and the regression model, right? So the R square is 0.7192, which is exactly this one, okay? And the p-value is is less than 0.0001, which is exactly this value. So you see that those tests are related, definitely very related, right?
Wilson, in this last regression, when you add this I letter, we can understand if there is a difference between the first categorical and the second categorical.
Great question, Karla. I wasn't going to mention this because it's going to be a very long presentation, but yes, you're right. Now that you have mentioned this, so the syntaxes of the regression model, this is just for teaching purposes. Regression, Y and X variable, okay? But in real life, you have to tell STATA that this is going to be a categorical variable, okay? So this is what the I point means. By I point, I'm going to say to STATA, look, I'm going to run a regression model, and my dependent variable is going to be birth weight, which is continuous, but my I've just decided to categorize my second continuous variable, the independent one, and just to let you know, STATA, that this variable is categorical, is not continuous. And as you can see here, the interpretation is different. And this is what we call, this is going to become more complex, but I'm still able to explain to you this. So you see the two outputs are completely different. If I run a regression model with the I point and without the O point. So you see that still the F-test is significant because it's a very good model anyway, but STATA is not doing the same thing because the F value is the same here, as you can see. The F value is 60.20 and 60.20, right? And then the R square is going to be 0.7192, and then here 0.7192. It's exactly the same, but the interpretation is different. Sorry, I'm just comparing the wrong ones. Excuse me. And I just try to compare this one with this one, which is Karla's question. Sorry. So you see here it's exactly the same. It's exactly the same, yeah. But here the F-test is 60.20 and here the F-test is 120.26. Why? Because you didn't say STATA here that this variable was categorical. So STATA is understanding that this variable is continuous, and it's not, it's categorical, right? So this is what we call in the STATA language a dummy variable. So let me just write here. I dot equals to dummy variable. This is what is called dummy variable. So what does it mean? That the interpretation is still the same here. I mean, my model is still valid here. I can say this, that for every 100 increase of maternal blood pressure, the baby weight is going to increase 443. But then, as Karla said rightly, the interpretation here is going to be regarding the category 1. What is the category 1? Let me see here. So the category 1 was this one. So STATA is going to compare this group with this one and this group with this one, and it's going to report a beta value for that, okay? So in this case, that means that compared to the basal one, to the basal variable, which is less than 100, compared with those patients that have less than 100 milligrams per deciliter, the increase on the baby weight is going to be 897, but compared to the basal one. I don't know if you understand the interpretation, because it's different from here. Here I'm saying that for every increase of 100 is going to increase 443. And here I'm saying that compared to the one variable, which is those patients having less than 100 milligrams per deciliter, compared to those patients, the patients with variable 3, which is more than 100, are going to increase 897 grams. Yeah, and same interpretation for the category 2. It's difficult to explain to you, but I don't know if you can understand my explanation.
Yes, Wilson, I guess it's important because sometimes you think that the variation is the same, but in fact it's not. And
it is not.
Yeah,
yes.
it's important to understand, and if the statistical test show it to you, it may has a clinically significant result.
Exactly. That's exactly my point. So let me just see here. Yeah. Where were we? Yeah, so only for teaching purposes, I'm going to stick with this model without the I point, because otherwise it's going to become more complicated. I just wanted to explain to you, this is just the basics of regression. So we've discussed the sum of the squares last week. And we say that this is exactly the same that ANOVA does for us. and the sum of the squares, the model is going to be the between group variance if we were talking about variance, and then the residual squares are going to be the within group variance. But this is just in case you're running an ANOVA model. But the output, exactly, the numbers should be exactly the same as the ANOVA. And then you just need to calculate the mean square, which is this one divided by 1. So that's why 53, whatever it is, divided by 1 is exactly the same. And for example, for this one, if you divide this value, let's divide this value, you divide this value over 48, which are the degrees of freedom. I did explain to you the degrees of freedom the other day. And then this is going to be 44,687, which is exactly this number, which you can see here. And same for this one, okay? So you just need to divide this by this, and this is you're going to obtain the mean square, which is the variation. In other words, this is going to be the total variance in ANOVA or the total dispersion in linear regression. This is going to be the residual dispersion for a linear regression model. And this is going to be the factorial dispersion that I did explain to you. So you understand why I was explaining to you this. Hopefully it will make sense now.
Yes, Wilson.
Perfect. So the number of observation is my sample size, about 50 patients. And then what is the F value? The F value is the comparison between the model, the variance of the model or the dispersion of the model and the residual. This is just a ratio, okay? So if I take this number, I'm going to take this number, display. I'm going to take exactly that number and I'm just going to divide. So this number, remember that this is the factorial dispersion. I'm going to divide my factorial dispersion by my residual dispersion. Let's see. So it says 120.25. So can you see this number here? This is the F value, okay? So then the next step for this, you just need to go for internet and look at the F table. I displayed to you last week how to go through there. So you just need to look at the F table and for those degrees of freedom, what the P value is. And then obviously this is going to be very significant because my model is very good, yeah? And then the R square. So the R square, I displayed to you last week that the R square is the how well my model is explained. My model is explained by the independent variables. In this case, there's only one independent variable, right? So how do you calculate the R square? So the R square is going to be this number divided by the total dispersion of this data. So you see here that my output is here 0.7147, and this is exactly this one, 0.7147, right? And then the adjusted R square is an explanation. It's just an adjusted R square value when you have lots of explanatory variables, lots of independent variables included in your model. So because some variables might not add information to your model, so you should always look at the adjusted one, okay? Adjusted R square. There is a equation for this, which is not really difficult, but this is not the case to explain to you all the equations, okay? And then let me show you something as well, because I did say that the Pearson, I'm going to run the Pearson again. Pairwise correlation, and then the Y variable is going to be, Y variable is going to be this one, and then the other one is this one. So my R value is 0.8454, okay? And this is the R value, but if I say that the R square, if the square of this value, actually, I can demonstrate to you. I'm going to take this value, and I'm going to square this value, okay? So the square of this value is going to be 0.7147, which is exactly this R square. So you see the relationship between the R for Pearson and the R square. It's exactly the square, actually, of the R. Do you understand this? Right. And then the last one I'm going to explain to you is the root of the mean square error. And the mean square error, this is the mean square, and the error is the residual, right? So the root of the mean square error is a measure of the accuracy of your model. And the mean square error is exactly this one. And if I say to you that this is the variance, the residual variance, so what would be the root of the residual variance? What do you think is the root of the residual variance? As it says here, the root of the residual variance. What exactly is the root of the residual variance? Does anyone know? So you remember when I explained to you, the root of the variance is the standard deviation. The standard deviation, okay? So the root of the mean square variance is the standard deviation of your residuals. The standard deviation of your residuals. This is this number, and this is a measure of the accuracy of your model. And I can demonstrate to you that if you take this value and you take the square root of this value, so it should be exactly 211.39, which is exactly this number, okay? 211.39. And then I can explain to you every single number here, but unfortunately we are running out of time. And then I'm going to explain to you very quickly what the confidence interval is, okay? So the confidence interval, as I explained to you, is given by the coefficient, the beta value, plus or minus the standard error of your beta value coefficient, okay? Multiplied by the t value, but not this t value, but the t value for this, for n minus 2 degrees of freedom. In which case, in my example, the t value for 48 degrees of freedom, right? And so you will come up with a number here, looking at the t table on internet, and then you just need to calculate this, as I say, the coefficient plus or minus the standard error multiplied by the theoretical t value, which is not this one. This is the t value informed here is for your sample, but not the theoretical one. And based on that, you're going to construct your interval, your 95% interval. So that means, and that's my answer for your question, the 95% confidence interval means that the coefficient is given by 443 grams of weight, but there is an uncertainty about this, obviously, And STATA is saying to me that with a 95% of confidence, this value actually is going to range between 362 grams and 525 grams. Right? Any questions so far? Is it too complex, too difficult?
I guess it is difficult, but in this space, the numbers and the interpretation, I guess it is our main goal, right, Wilson? The interpretation and understanding what STATA and the statistical analysis is showing us, it becomes more clear.
Yeah.
We should try to understand what the meaning of this value, to not be so scared to see a lot of numbers and doesn't really know from where they come. But I guess it was a wonderful lecture as always.
So as you can see here, long story short, you don't need to look at all the whole output. You just need to look at the adjust R square, your significant level here for your model, and then all this line is very important for you to understand from the clinical point of view. If I have 3 minutes more just to answer your question regarding because this is a difficult one as well. Let me think. There is another comment which is predict, actually. And predict what? You are going to predict the residuals. So predict, let me see here, yeah. I'm going to call this variable, for example, fitted what? Fitted beer weights. So if you, this is just the name of my new variable, predicted fitted bird weight, and you, if you look at my data set, STATA just generated these are the theoretical values. The theoretical values for every single patient. As I explained to you, you must have theoretical values in order to run your straight line, because you don't have the theoretical values, you can't really construct your line, okay? And then because I've got my predicted weight for every single patient, so I'm allowed to run my my graph with the line, which is, it would be again is scatter, the y variable, and then the independent. Oh, sorry, this is going to be the predicted fit bird weight. Let me just bird weight, and I'm going to do this. And then I'm going to say to STATA, let's run this. See what happens. Okay, so let's try again. Predict.
Wilson, can I ask just one last question?
Yes, sure.
I'm sorry, below the letter T in the table, what does that mean? Is that the degrees of freedom? I think I didn't get that part. The 10.97 in the first row below the T, what does it represent?
Yes, I'm going to explain to you in a couple of minutes, okay? I'm just trying to construct my line based on my residuals, based on my predicted values. Sorry, for some reason I can't.
Wilson, I'm not sure, but I guess your predicted value was based on categories. That it could be the problem, because I'm not sure, but on your data set, it seems that we have only 3 different predicted values.
You might be right. Oh, I see what the error is here. Sorry about this. So this is what I wanted to show you. Finally, sorry. So because I categorize my variable, this is going to look completely different here because they are categorized, but still you can build a regression line because there is actually a good correlation and there is a linear trend between the categories. This is what I wanted to show you. But in order to draw this line, you have to first predict your values, right? You have to first predict your values. And a couple of things before we leave. The first one was Karla's question. Let me see, predict, and then you can actually predict the residuals here as well. You put a comma here and residuals. Sorry about this. So this is going to be residuals. For example, this is the name of my variable, and then you just go to the browser. Stata is a little bit slow now. I don't know what happened.
Even for Stata, calculation is not easy.
I just wanted to show you this very quickly before we finish this presentation. I don't know what happened here, but for some reason, Stata is not going to do anything. Oh, I don't know what happened. Maybe Stata is just overwhelmed. Yeah, I just wanted to show you. And anyway, so oh, there we go. So you see the residuals here, and then Karla asked how to actually the residual is just the difference between the bird weight and the fitted weight, between the observed weight and the theoretical weight. So 2930 minus 3131 equals 201. You understand why? Because this is the difference between the observed values and the theoretical values, okay? So you just need to look at, take this variable, which is my residual, and then see where or not and these values are normally distributed. So I'm going to do this quickly. For example, with Shapiro-Wilk, and then residual. So you see that it's normally distributed, as I explained to you a couple of weeks before, yeah? So it's normally distributed, which is good. And this is one of the assumptions. And this is the way to prove that the residuals are normally distributed. Okay? And then regarding the other question, the t-value, so this is the theoretical value, and then you just need to compare this against sorry, this is the experimental t-value. This is my t-value for my data, and then you just need to compare this value with your theoretical value on the t-value on internet, and you will see that there is so much difference for n-2 degrees of freedom, and therefore the p-value is going to be really significant. But the 10.97 is not included in the calculation of the 95% confidence interval. This is going to be the theoretical value for 48 degrees of freedom, right? And so I think I'm finishing with my presentation now. So thank you very much, everyone, for coming again. As I say, we got a very highly motivated group of students here. They are still 16 participants who survived to my presentation. Thank you very much. I'm really hoping that you have learned something about linear regression. And this is not an easy topic, but at least we managed to cover the most basic concepts before understanding all more complex models of regression. Thank you very much, everyone.
Wilson, thank you very much. It was an amazing lecture. Yeah, I loved it. Very good.
We can't thank you enough. It was amazing. Thank you so much, Wilson.
Thank you very much, everyone. See you soon.
Bye-bye. Thank you so
much. Bye. I will send you as fast as I can the presentation, right? Thank you so much.
Thank you. Thank you everyone for coming, and we'll see you soon.
Yeah. Bye.
Bye-bye.
Bye-bye. Thank you.